Okay, a little bit of debugging. I think we might be streaming now. Looks like YouTube's got video. Trying to do the thing where I'm simultaneously streaming to YouTube and Twitch again, and still ironing out some of the bugs from this setup. I think that last little glitch was the firewall trying to block the Nginx process on the machine that was doing the streaming. Okay, looks like we've got video on Twitch and video on YouTube, and they're both muted. So, all right, looks like we can get this stream going. Make sure that I have announced this on Twitter. Tuco really wants to play. Let's switch to the Tuco camera while we're getting this thing started. Hi. I think we want this one. Hey, cat. So this is actually an electronic stream, but I also happen to have a cat who really likes to play with these nylon bolts, so it makes a nice interstitial when we're getting stuff set up. Don't mind my messy pile of cables. This is the clean side of the shop, and that's the messy side of the shop. Just checking to make sure that we have the announcements on Twitter. It looks like that worked out. Cool. Oh, and now we've got the chat. Hello, everyone on YouTube. And I'm going to try to keep an eye on the YouTube and the Twitch chat. I don't know how good I'm going to be at this, but we'll see how this works out. Yeah, oh, I just noticed the question in chat, whether Tuco is frustrated that he can't get to my audio interface anymore. So yeah, that little M audio box there handles all the audio mixing for the streams and for the shop in general. And it's also quite nice and warm, and it used to be on my desk. Tuco really liked hanging out on it, but part of the reason for this change in organization, well, part of it was I got this free piece of furniture that was about the right shape for this, and part of it was to consolidate all the cabling, because a lot of this equipment was kind of spread across this whole side of the shop, and it made a lot of sense to centralize it once I got to a certain density of interconnect, I guess. But also Tuco would sit on top of this thing and just totally mess up all the level knobs. So, you know, I'm not going to blame him for all the audio level problems, but there were at least a couple of them where I'm pretty sure he was napping, and then some of the knobs on the right especially got turned all the way down, or, you know. So I'm hoping he still has plenty of warm spots to choose from. He has at least a mat to hang out on. So yeah, apologies for the gap in streams for the past, what's it been, a couple weeks. A lot of little things, a trip to Portland to meet my new coworkers face to face, and it turned out to be pretty snowy in Portland. Some of you might have heard that some snow happened. But yeah, that was actually really cool. Let me see if I can share. There is a small video clip I wanted to share just because it was kind of cool, and I think some of you might appreciate it. Hey, maybe I'll play fetch with Tuco while I get this up on my phone. This cat, if you can tell, is kind of hyper. He really pretty much always wants to play with those bolts or something else. Let's see. Okay. What is this? That's not supposed to be a black screen. Might have to restart the AirPlay server. Okay. To go. All right, I think part of the, so the point I was trying to get to was a bunch of stuff has changed in the setup, and so yeah, there might be a little debugging in this broadcast since the last couple of these I've been making, making changes to the setup. One of the major changes was swapping out the computer for something actually fast enough to handle HD video, so that's why the quality is so much better. But then, rearranging everything. And then, as you might have seen either here or in the Twitter, I have this really amazing new oscilloscope. It's a Keysight 6000X series. Yeah, 1 gigahertz, 20 gigasamples. There's really a lot to like about it. It's like by far the nicest instrument I've ever owned, and it was a really generous gift. And yeah, it's a lot of what I'm going to be working with today in this stream. Since I've been doing these voltage glitching experiments, and before this trip to Portland, where all the snow was happening, I had collected some data with this experiment that we're going to be looking at, and the data was, I hadn't gotten around to writing a script to do some kind of graphical analysis to see, like, really how noisy the data is. Where, I guess the noise in this case is, how reliably can I pick kind of a particular glitch side effect? If I find something I want, how reproducible is that? And in the current setup, I think the answer is not very. So I still kind of want to quantify that, since that seems useful. But having this faster scope also opens up some new avenues of exploration. So whereas before I was thinking I would have to do kind of a statistics-based approach where I just collect a lot of data and I try to find correlations between the states I want to get the CPU into and different configurations for the glitching hardware. I think I can do better now and actually try to dump out some more information from the processor in real time and catch the glitch as it happens and try to look at, in the time domain, what's actually going on near the glitch, and how can I make that part of the power waveform more reliable. So that's like my kind of actual goal right now. Hey, Tuco. I've also got some sub-problems to deal with. Well, a lot of what I've been doing this week is sub-problems, trying to kind of get everything set up to get video capture for the scope and to kind of tidy up all the wiring and change my setup around so that I can probe it using the faster scope probes. And so I still have some unresolved questions there in terms of, how careful do I need to be in terms of probing these signals. I've got some really nice low noise traces from, using the ground spring clip on these and just like, using alligator clips to hold the probes and position them all in just the right locations. But, that's also pretty precarious. So I'd like to add some little, loops on my circuit boards that I can use to hold the probes more securely. Just generally need to get the test set up a little bit more stable so that I can actually get meaningful measurements out of it. But yeah, really, really happy with what I'm seeing so far. I'm seeing stuff in the power waveform that I just couldn't see any of on my old 100 megahertz scope. I would still like to, so I have this pile of data which we might try looking at. It's like exported from the Chip Whisperer, so it's a bunch of Python pickle files. And I can load them back into the Chip Whisperer software, and I think we can just look at them as a table there. But what I'd really like to do is have like a graph where I have the parameters for glitching on the various axes and kind of display a heat map of the various success rates I'm getting for the different parameters. Oh, Tuco. So yeah, scope, all the video stuff too. Well, so you might have seen it as I was flipping through the channels. I've got the video capture rig on the scope too, which is, it's got a VGA port on the back, which has been handy. And it puts out like 800 by 600 VGA, which is fine, but I you know, that needs some conversion steps before I can capture it with the rest of the stuff. Hey, Tuco, where did you just put that? All right. So I think first it makes sense just to get this into kind of a baseline state where it's running, which I think is pretty straightforward, but I'm just going to get these probes out of the way momentarily. And then we can verify that this works, but then I think maybe the immediately next thing to do is to solder on some better probing points. But I guess that comes back to the question of the best compromise between how easy it is to probe around on here and the quality of, because some of the signals I'm interested in are getting up into the few hundred megahertz where I really need to care about probing. So these little spring clips, if you haven't come across these before, they're super handy. I would always end up making something like this myself out of just some wire. But these relatively fancy probes come with something that's like made of spring steel and really purpose designed. And you can adjust these. They move pretty easily in one direction, but not in the other. Anyway, we don't need the scope on the screen just yet. Yeah. So the nice thing about this is the ground has a very, very small loop area here. You can pick a ground that's right next to the signal you're tracing. This is also like a real pogo pin at the end. It's spring loaded. So, if you push this against something, you can see it. Yeah. So now both of these, if you just apply some pressure, will actually make a nice spring contact. So that's what I had been relying on. There's actually an accessory they make, which I really like the idea of. I had like a version of that here. Where did I put it? Yeah. Oh wait. Let me show you what they would like to sell me. Oh yeah, this is the manual that I've been going through for the scope. Lots to learn. But let's see. Oh, why are you on that monitor? Yeah, so they call these things probe positioners. Yeah. And so there's some really fancy ones, like, like you can see this little tiny picture already here. There's like, fully articulated arms, kind of like what I have for my camera, but like 10, like maybe 5 times the price, I guess. Are any of these pages going to load? I just changed the network around here too, and I think some of the computers have an old DNS server cached. So I might actually have to kill the browser. Yeah, so that was the other change in my my setup around here, because I had been on Comcast cable, which was fast enough just barely to stream one pretty good HD stream up. So I've been using that, but as some of you might have seen in the previous streams, if I forgot to kill the backups, then it would just totally die. It didn't have nearly enough upstream. And to do multiple streaming, like to Twitch and YouTube, I had to stream to an Amazon EC2 server and then have that stream. So for only slightly related reasons, I ended up ditching Comcast here. And I found out that fiber was available in my building for about the same price as cable and like 10 times the bandwidth. So that's what I finally got on like today, but that required a bunch more equipment, switching around, getting a new router and then moving the moving that video distribution server from EC2 back here. Anyway, I think they call this yak shaving. So yeah, okay, Keysight has these various options here. There's a really fancy one, which seems like something I probably would not pay for, but I would be really into like designing a 3D printable version of this. I don't know why that's not loading either. But anyway, this is the one that seemed pretty reasonable. But, okay, the price is behind there. Oh man, $64 for, it's not even like spring-loaded, it's just a piece of plastic with rubber tips. So I was like, I could just 3D print something like that. So I was going to get out a CAD program and design something. But then I remembered I have a bunch of these like photography and like woodworking kind of clamps around, so they've been actually working all right. You just clamp them on here and then they don't clamp on quite as easily. You have to get this just right, but and then the weight of the probe just kind of holds it down. Anyway, still kind of precarious, so and then I was holding the probes with this kind of octopus arm thing, which is pretty awesome, but also kind of precarious. So yeah, and I think, they make various accessory kits that are designed for this sort of thing, where there's like a temporary, socket that you can plug the probe into. I was researching some of those. There are various degrees of fanciness. There's some that are like little coax receptacles that you solder onto the board, which I'm sure are good to, some number of gigahertz. And that's overkill, but those are also like a couple $100 each. And then, there's various, there's one accessory I think you can plug the probe into this thing that has two short little wires that maybe that would work better. But, I think for my uses, these two little, sharp points are actually kind of nice, assuming I give them, a relatively mechanically sturdy, stable point to kind of sit into. So yeah, I think I'm going to try doing something where I just, kind of stabilize the area that I want that to sit in with a little loop of wire. But let's try to get an idea of how necessary that's all going to be. All right. Just throw everything. All right. Okay, cool. So I've described this setup a bit on earlier streams. Just really, come on. Is that not the right button? That's the right button. Great. Yeah, so just briefly here, I've got this kind of stand-in for the device under test, developing a glitching technique that works against this particular microcontroller, and it's one of the Tiva T-series, or C-series from TI. And it's mostly interesting because it's sort of an Internet of Things class microcontroller that has onboard Ethernet, some security features, usually would not run like a full operating system. So kind of an interesting device to develop techniques for analyzing proprietary software on. And then this is the same board, but acting as a peer, just so that I can have two boards speaking the same slowed down version of Ethernet, because I'm trying to underclock the whole thing to make it easier to analyze. Then here's a Raspberry Pi, which is actually driving the slow Ethernet, and that's running a proxy server that lets me talk to it over my shop network. And then the chip whisperer over here is generating the clock signal that drives everything. And the clocking for this whole thing is kind of complicated, and I think is maybe the source of some of the problems. So I'll talk more about clocking in a sec. It also does some data capture of the power rail through this coax, and it generates the trigger for glitches. There's another FPGA on here. This is a lattice iStick, and that's doing some clock management to generate another clock signal that these boards need. And then this board on top is sort of a glitching amplifier that's basically a half-bridge MOSFET driver that can pull the power rails to a couple of different levels. So, various things I'm interested in measuring here. Now that I have this fast scope, I can take a much closer look at how well the glitch pulse is shaped, because I've seen some evidence that maybe there's something going slightly wrong with or when I say wrong, I mean inconsistent with the way the chip whisperer is generating the glitch pulse. So if that's actually the case, maybe that's a problem I can track down to improve the overall consistency. And I can kind of trace the glitch itself to try to make sure that I'm generating the most consistent electrical pulse I can. And then I also really want to find a way to analyze the consistency of the glitching results. So, the various tests I can do for that, but the kind of, the most interesting one I have in mind, I think, is to add some instrumentation to the firmware to kind of continuously dump out the state of this loop that I'm trying to glitch over GPIO. And then I'd like to watch in the time domain what happens with the chip's time base. Since I can't directly observe the processor's clock, a lot of the complexity here is in trying to kind of recreate a clock that matches what the processor has. And I'm pretty sure I'm not doing it in a consistently phase-aligned way right now, just due to having kind of a fractional divider between the two pieces of the system. So that's something I'd like to look at, and having some external GPIOs following along with this loop. If my glitch ends up disrupting the operation of the PLL, I can maybe use those GPIOs to keep track of, what that disruption looks like, how long it takes to recover, how consistent the recovery time is. So those are the kinds of things that I want to get answers for. Anyway, I need some tea, so I'll be right back. But here's Tuco in the meantime. Let's see if I can get this better view. Oh yeah, good cat view. All right, thank you for bearing with me. Oh, another random slight setup improvement that I like showing off. Okay, it doesn't look like much right now, but there's a doodad over here. This is an experiment in trying to have another wireless camera option. So some of you might have seen on some previous streams, I'd been like carrying around an Android phone into the closet where I do machining and 3D printing. And, that provides pretty good video quality, but it also is prone to kind of just like stop working every once in a while, when it loses Wi-Fi signal. So I thought I'd try out like an analog video transmitter like you'd use for an FPV racing drone or something like that. So this is, this is just a pretty small camera that records locally in 1080p and also has a composite video out. Then there's a little DC-DC converter to power the camera. Then there's the analog video transmitter and just a nickel metal hydride battery pack and a clamp. So I can just stick it on things. And then, so it's a source of some pretty weird glitches, and it's probably a little bit out of sync between the audio and video, but, it is what it is. But the main benefit of this is that it should have pretty good range, and then that because it's analog and, unidirectional, it won't have problems where it just totally stops working. Aww. And of course it would be great if there's some version of this that Tuco could wear. I might have to look into other video transmitter solutions because this particular one is pretty power hungry. So even if I made something that was safe enough and light enough for him to wear, I think it would just get too hot. Because it's like, I think it's like 600 milliwatt transmitter. But yeah, maybe something with digital video for him. Anyway, yes. Oh, and that was like 6 AA batteries, which seemed to last 2 hours, a little over 2 hours with that setup. Okay, let's get some work done. So we've got this VM. So the first step in getting this going is to run this script that configures the chip whisperer. That'll give us a clock source for everything else. The other devices on the system don't really like existing without the clock source. Wow, Tuke's pretty into something outside. All right. I think I just need to run this, and this will set everything else up. Okay, except for that. Let's actually connect the USB device, and then maybe that'll work better. All right, so this should be set up to run an experiment already. We can just double check the clock rates and everything. Yeah, so right now this is generating a 27 megahertz clock. This is, and the rate is not really special. This is not the rate it's designed to operate at. This is just the slowest I can make it without the Ethernet adapter going into a state which seemed to be unrecoverable. Yeah, I debugged it a lot to try to get this number lower, but as far as I can tell, this is limited by something intrinsic to the way the Ethernet MAC is, or the Ethernet PHY is designed. That there ends up being some mismatch between the characteristics of the digital part and the analog part in the DSP system, and then it just starts oscillating. But this, as far as the rate goes, is set up to match the internal frequency of the device under test. So part of what well, pretty much the entire purpose of this FPGA on the iStick is to divide this clock again to the external clock rate. And it's really just trying to do the inverse of the clock multiplication that happens inside the system on a chip. But yeah, that introduces some weird issues where, you know, the clock can have a lot of different phase relationships, and that might be part of the problem with consistency here. All right, so speaking of that FPGA, I think the software that I want to use to load that is outside the VM. So well, I was going to show these LEDs that are like right behind that circuit board, so maybe I won't bother, but... Oh, right. Come on, wireless. We went over this before, but this program that loads code onto the FPGA goes directly to the FTDI device, not through the Apple FTDI driver, so I've got to unload it. And man. I think perhaps the receiver for this Bluetooth keyboard is buried in with way too many pieces of noisy metal. Alright, so after that, now we can load code, and you might be able to see that reflection, the flashing right there. That's just a light indicating the clock is good. So now we should be able to reset both these micros, and they should come up in a fairly stable configuration now that they have a clock. So the first thing we'll do there is SSH into the Raspberry Pi and get the proxy server running. Alright. Alright, so now this is running on the Raspberry Pi, and it's basically acting, it's like a GDB script that's acting like an Ethernet driver and forwarding packets to a network tap device. So now when I plug the Ethernet cable in, which I had been avoiding doing previously due to DC bias in the system, I was expecting this to come up. Oh, that's right. I don't have that power supply turned on. So the power light came on here due to exactly what I was just mentioning. I was like powering this through the Ethernet cable because I've removed all the DC blocking. Let's not do that. Instead, let's power it up through this. And this is a relatively high voltage of 12.5, because that's what I can run the MOSFET drivers off of to get the fastest edge on the MOSFET gate. So now this processor should be running. Attach that, and we've got a connection. So yeah, a lot of work went into getting that to connect so quickly, since one of the things that I want to do to get a reliable glitching setup is before every experiment I want to do a hard reset on this board. So I did part of that in, I think, the last stream. I put in this transistor so that the chip whisperer has a GPIO, so that under software control, and in fact there's like a module already built into chip whisperer that like pulses a GPIO pin before each test. So I could just use that to, through this transistor, pull the reset line down on this board to reset it before each test. But the problem with that was Ethernet, especially with auto negotiation, is not really designed to establish a link really fast. And it was even worse because I'm underclocking this by like 1/5 or so. So, imagine an Ethernet link already takes like a second to come up. Now it's like taking 5 seconds because I'm underclocking it. And that has to happen for every single glitch experiment I run, where I want to run thousands and thousands of these. So that's a bummer. So yeah, that ended up being an interesting fix where even after I was configuring the Ethernet driver and the Ethernet MAC to send or to disable auto negotiation at the Ethernet PHY level, it was actually sending the Ethernet PHY. The registers were configured kind of weirdly so that from the MAC's point of view, auto negotiation was off, but from the PHY's point of view, it wasn't using the results, but it hadn't been explicitly disabled. So I can't tell whether this is just like a weird feature of the chip or an actual bug or what, but if I actually go through and specifically write the registers directly to the PHY to disable auto negotiation, then it comes up really fast. So that's something I'm grateful for. Those little configuration changes that make this work better. So now I can just reset this and link down, link up. In fact, I was doing this experiment before where you can actually, if you time it right, you can press reset in between pings, and it'll still you won't miss any packets. So, come on. So for the network configuration here, I have wireless on, although I'm not actually using it. Here's the Ethernet that I'm communicating with it over. And then this tap 0 interface is what I'm actually speaking to the device under test with. So tap 0 here is actually this microcontroller's Ethernet adapter. And the script running on the Raspberry Pi kind of does this weird thing where now the Raspberry Pi has the microcontroller's Ethernet adapter as something that's effectively local. So if I ping through there, you'll see the GDB script kind of spewing out the debug information for that. So yeah, I'm resetting the processor after each ping response. And I guess it's possible that somebody's retrying. Let me see if I just hold this down for a couple cycles. You can see it misses a couple packets. Yeah. Yeah, okay, so you do have to time it right. But yeah, it is possible to reset it in between pings. So, so yeah, bringing up connection instantaneously, pretty nice. So that helped a lot. It helped me collect more data at least. So as far as data collection goes, let's go to the next stage here. So if I'm still on the Raspberry Pi, I can make requests to, to the web server running on that address. So instead of just pinging it, well, like for example, I could nmap if I want. Let's try. Do I dare scan all the ports? I think I'm going to have to do something like that. I've never tried this before. I don't know if that's actually going to work. Yeah, I might just be doing something wrong there. Anyway, the interesting thing to do at this point, the way it's set up, is to download really anything from HTTP on port 80, because that's where the experimental code is hooked in right now. And so that runs this little experiment where it just has a lot of loops that are intended to be broad targets for glitching. And then these values, if the glitching was successful, will be something other than 100,000. So that's normally just adding 1 to a counter 100,000 times. But if the process of loading or storing that value or the number of iterations gets corrupted, then that value will be something different. That also has the side effect of sending out a trigger signal every time this runs. So the way this test actually operates is first the chip whisperer sends the reset to, give us a clean slate and a known hardware configuration for the device under test. Then it actually initiates the test, after it's sort of armed the acquisition and triggering and glitching systems. It initiates the test by sending this HTTP request. Then the actual trigger that both the acquisition and the glitching are based off of is a GPIO that comes back from the device under test. Just some GPIO code that I've inserted right before the glitching target. And that edge is what the chip whisperer actually uses for its acquisition. So that's also the same signal I want to trigger the Oscilloscope on. And I think I even want to be looking at the quality of that signal to make sure it's got a good edge that we can reliably see. Everything should be synchronized to the chip whisperer's clock. Actually, just as I said that, I realized I'm lying, because a lot of this is more complicated than a regular chip whisperer setup because we have these different clock domains. And I think some of the problem here is in trying to cross the clock domains. Where to go next with this? Let's go back to let's avoid going too deep into too many rabbit holes at once. Okay, so the automated test setup was over here. And so if I click this button, it should do all the stuff I just talked about. So it sends the HTTP request, chip whisperer gets the results down here in the UI, and you can also see the results of this glitch happening. So you can also tell, so the data here looks pretty weird because there's like a beat frequency happening between the different clocks, and I think this sine wave here is actually related to the slower clock that the FPGA here is generating, and that's the input of the PLL on the device under test. I thought that might have been a measuring artifact of the setup here, but when I started looking at it on the nice scope, I was seeing the same thing, so I think that might actually be more real. So that's what this frequency is. That's kind of just annoying noise. But if you look at the envelope here, like modulated on top of that, I think this envelope is actually giving us some good information about what the CPU is doing. So this is correlated with the activity of the loop that we're actually looking at. I think I might turn on the other video recorder so I have some better feeds of all this without the picture-on-pictures on top. In the meantime, enjoy this very sunny cat. Okay. Yet more yak shaving. I still don't have an easy way of managing all the video recording apparatus from this particular spot, since a lot of it's running on the other computer. Okay, so this, so I was just saying that this waveform here is, this sine wave is, I think, related to the slower clock that we're generating, but then the modulation on top of it is actually related to the activity on the CPU that we care about. So then the glitch is happening, and we'll get a better look at this on the new scope, but what's effectively happening is a series of short pulses that are they're at the same frequency as the CPU clock, but they're phase misaligned with the clock by an adjustable amount. So part of what we're doing with the glitch is kind of creating this interference pattern between that glitch waveform and the all the kind of clock related noise that's already in the processor. And I think that pattern might be important in actually trying to track down the behavior of the glitch in the time domain. So some of what we're going to see here is related to the actual waveform the chip whisperer is generating, where it switches the glitch on and off in sync with the CPU clock. Then some of this high frequency noise here is actually related to the MOSFET drive. And it might be either the MOSFET drivers or the actual power supply rails ringing during that switch. And so that might be helping, it might be hurting, I'd like to know. And then afterwards, you can actually see the power supply rails ringing. I think that's what this is. It looks like a similar frequency to here, but I think that's actually the power supply rails, and we can take a closer look at that on the other scope too. Then during this period, I think the clock is actually stopped. I think the VC or the PLL on the processor is no longer running. Let's try to get that more on the screen. Okay, so this kind of noisy stuff is the processor running normally. The glitch happens, then it doesn't start running normally for a while, and when you run multiple experiments, one thing that has me concerned is that the time it takes for the processor to resume normal operations seems to jump around quite a lot. And this is with, let's make sure that this is not changing parameters also, because that would also change what we're seeing. I don't think that was changing parameters, but let's just turn this off. So this is the tool that helps you automatically search for glitch parameters, and I'm just making sure that it's not changing anything intentionally. So if I had a nice stable setup, then running it with the same parameters should just keep giving me really reproducible results, both in terms of the glitch's effect and in terms of what we're actually seeing on the power rails. And well, so there's stuff like that. I've been noticing those, every so often there's this huge burst of noise. Don't know where that's coming from yet. It hasn't been a huge problem since they're relatively infrequent. But this thing here is more concerning, where, let's see if I can get this on the screen better. Yeah, just this thing moving around in the time domain so much seems like it might be a problem. Let's keep capturing. So when it starts back up, the trace seems like it has a relatively consistent shape, but so one theory about what might be happening is that the glitch is causing, some analog component in the clock synthesizer on the chip, the VCO, to just run out of range for a while, and then the filter kind of has to get back into range before it starts again. And so, if I'm doing something like that, then maybe I can find like a better way of generating the glitch effects that doesn't also introduce so much unpredictability into when the glitch's effect is going to happen. That's really what I want to do, is to have the most reproducible control over the timing and the shape of the glitch as I can. Alright, so as you can tell, none of these were really useful, but I'll try to load some of these bigger traces just to get an idea of what a useful glitch looks like. So this thing has a recording feature down here. Alright, just gonna grab the biggest file, one of the really long traces I ran. At some point they got big enough that the software started having trouble with the data table, so this might be one of those. So I might end up having to pick a smaller one. Actually, I've not tried loading them back into ChipWhisperer yet. I was assuming that the way I would analyze these would be to write a Python script that just aggregates all the data into something I can plot. That might take a little while to load, so maybe while that's loading I can just look at the file. Okay, let's grab a really little one first, just as a small sample. So this is the ASCII pickle format for Python. If you haven't come across these before, it's like a serialization. It's basically a little program that Python will run in order to construct objects for you. It's intended to be a convenient way of storing stuff to disk. You can see it's like building an object with some strings in it, and this is the data that we got back. I assume some kind of timestamp. And really, it would be more convenient to have something like a CSV, but or like a JSON, but I'm sure it's easy to convert. This process is sitting there trying to load this file. But the way these are intended to be used is with the pickle module in Python. I think I want cpickle. Yeah, so it's just like pickle, cpickle.load. And let's just grab a really big one. This one, maybe. Oops. That does not seem like the right file. Oh, unless these files have lots of records in them, which might be the case. That's probably the case, actually. So this probably is going to be something like, I open the file, and then repeatedly call cpickle.load on it to get records out. So it starts with some header stuff. And then these are the actual experiment results. So like if you're in Python land, this stuff is as easy to use as JSON. Not nearly as secure, but you know. So this success criteria here is evaluated according to the little code snippets that you can insert into the glitch window here. And then these are going to be the settings that I would end up wanting to graph. So basically I could just use any kind of plotting tool to look for successful results. Well, to plot successful and unsuccessful results in like different colors or with different symbols, and then look at the distribution I'm getting. I think what I was seeing was that they were not especially clustered close together. Like, what I want to be seeing is some parameters that produce mostly successful results, but instead what I'm seeing is some parameters that occasionally produce successful results and a lot of parameters that never produce successful results. So, and that's something I can work with, but it's not the end goal yet. So maybe I can do something just really quickly to print out some of these values to illustrate that. Maybe while the Chip Whisperer GUI is loading this, we can write a simple Python script to just process these very slightly. I think I might be running this VM out of RAM, actually. Okay, maybe I can make my point using a smaller file. I think that problem is related to the keyboard, but it could also be the VM. It's hard to tell with computers. Oh, and of course, sometimes when I restart this, I lose my clock, and so then I have to restart the clock. Oops. And often this does not survive. I've got to restart the network bridge too. Okay. It doesn't seem to have come up successfully. Maybe hardware reset on this board. That looks better. Okay, that's running again. Okay, so this is running. I would like to analyze this more. Before I get too ahead of myself, let's do this experiment where I show you the data that I already captured. Okay, maybe one of these not as big traces. That one's pretty recent. Let's try this. I think when I looked into why this was so slow briefly, it was something to do with the table control and the GUI, just like adding rows to that stuff. Okay, maybe I can let that load while thinking about how to do the probing on here. I've got this little SMA connector. I think I want to add a 50 ohm resistor so that I can have a proper 50 ohm termination into the scope to get the best signal there. I don't think I'm going to get good results using the 1 mega ohm impedance on the scope. That's like one of the differences, like the early branches in the decision tree for how to probe a signal. It's like there's the kind of low impedance matched path where you're actually transferring a significant amount of energy through the cable, but you try to give it a nice smooth path where the impedances are all matched and you don't have reflections. And so that hadn't really been an option before because my other scope doesn't have 50 ohm termination. Actually, I'm curious with the Chip Whisperer. I thought its impedance was, I'd been assuming that it wanted this. I guess I just hadn't considered a series terminating the line on the Chip Whisperer, but I should check its schematic because it might actually do better with a 50 ohm termination on this end also. But yeah, so the Chip Whisperer and probably the approach I want involves keeping the whole path 50 ohms all the way from the source to the scope, which I think involves sticking a resistor right there and then using coax to get it from here to the scope. The other option is to keep the whole thing pretty high impedance, and that's what typical scope probes do. I don't know if you've encountered this before in like trying to use scope probes in place of regular coax cables or vice versa, but regular scope probes tend to be very high loss cables. They're designed to just lose energy the entire way through in order to give them really wide bandwidth response, but very little energy actually makes it through, so that's part of why the impedance on the scope input has to be so high. So, one approach that I had been using to probe these signals pretty well is to just use this, and let's just try doing that for reference here. Wake up the scope. And this is going to be a little awkward, but all right, so that should be, I think I wanted that on yellow channel. Let's turn these off to get them out of the way for now. Okay. Okay. It's a little tricky because I want a nice low impedance connection both to the power rail and to ground, and I don't want to short it out with the very, very close by 3.3 volt rail. All right, and according to the nice little multimeter there, we've got the core voltage we're expecting. I think that nominally is, I've been remembering it as 1.25 volts, but maybe it is closer to 1.28 nominal. So we're already getting a lot of kind of bouncing around. And I'd been assuming that might have been related to sending out Ethernet link pulses. I'm going to see if I can trigger on that to get a better idea of what's going on. Oh, yeah. So this is so much detail I couldn't see on my other scope. And part of what I want to make sure I can do is, I think this is probably the best way I have of probing this right now is with, a nice, well compensated 700 megahertz passive probe, like right on the power rails there. But it would be more convenient if I could use these SMA connectors that I've already installed. So I think what I'd like to do is just kind of get a baseline idea of what this looks like, and then try adding that termination resistor. Well, one of them for each of these SMAs, preferably. The way I did that mechanically, it might not be super easy. Then anyway, compare that to what I get with the 50 ohm termination on the scope and see if that's at least comparable. Because that would be much more convenient than having to either hold this here or make something that this probe can fit into. So this will look really interesting on the FFT, I'm sure. We can see that's the kind of macro scale noise that we're looking at. And I'd like to track down where that's coming from. That might even be something outside. Well, let's see if this goes away when I hold down reset. Yeah, so if I'm holding the device under test in reset, its voltage regulator is still on, clearly. Yeah, and something that low frequency, I'm wondering if that could be coming from the regulator itself, although I don't know why a linear regulator would be giving us, waveforms in the couple of hertz range or whatever that is. Can we measure what that actual frequency is? Cursors. I still just barely know how to use this scope. All the muscle memory for my other scope is not the same. Oh, that's what I want. Manual. That's right. Huh. Yeah, I don't know what this would be. This is weird. Maybe some kind of flashing LED thing? Huh. Yeah, so that'll be interesting. Let's take another look at the higher frequency stuff, though, because that's what I care more about preserving when I change the probing setup. So, I think this frequency might be the main kind of modulated thing that we've been seeing on the chip whisper. Let's change this. I think I can get this to automatically measure this conveniently. was trying to apply this technique I'd seen in the manual for getting the measurement, or the frequency measurement, to grab onto just one cycle of the waveform, but you know, I do like being able to see the DC level, but this might be more convenient with AC coupling. Huh. Man, it's really nice seeing this like histogram of so many different versions of the waveform overlaid. Like, it's pretty much everything to like about an analog scope. I think what I want to do is just turn on persistence to make it easier to measure this. Oh, maybe I just want to low-pass filter this and then take a snapshot. Because I mean, it looks like it's pretty close to the frequency that my PLL is generating, but I would like to know with more certainty that it is that. Oh, wow, that's cool. That's got some more stable harmonics than I would have expected. Well, neat. All right. Can I measure directly off of that? I think that's giving me a pretty good measurement. So now if I think if I get measurement statistics, I can get a nice average of that. Tyler Tico's favorite birds. I know I saw this menu before. There is a thing that I can use to aggregate measurements over time. Here we go. How do I delete these? Yay. Okay, let's get a refresher on what all the clock frequencies in this system are supposed to be. freeze this display. Oh, I seem to remember there not being a dedicated freeze key, but that you can assign this quick action key to be a freeze key. Let's do that. Yeah, that's great. Yeah, and that is a satisfying measurement. Like, there's so much noise there. But, good signal. There we go. Okay, so our input clock was 27 megahertz. Let's also have a refresher about what this clock divider / multiplier is doing, since that is going to be important really soon. So basically it's a multiply by 5 and then divide by 24 in this FPGA. So if you hypothetically did that process with a 120 megahertz system clock, then you would get the 25 megahertz Ethernet crystal clock. So, I mean, this can't handle such a high frequency. It's intending to be underclocked, but that's the gist of what it's trying to do. So what we'd actually be doing is, instead of that 120 megahertz clock, we have a 27 megahertz clock. So then our intermediate frequency should be 5.65 megahertz. So that is not what we're measuring here. This 7.3 whatever is coming from something else, it looks like. Well, let's try getting the other clock up on the screen too to see if it's even phase locked with that. I mean, I don't see what it would be phase locked with, but all right. Anyway, I could get really deep into experimenting with that measurement, but I think first I want to see if I can get away with the 50 ohm instead of holding the probe down. I want to check what the input looks like on the chip whisperer, because if it's also 50 ohm, then I can just do the same thing for both, and it might improve my measurements there too. Oh, I just want the schematic. Is this having some DNS-related problems, maybe? Do I not even have Firefox on this computer? Oh, did I just make this default? No. Anyway. Maybe this is not a browser caching problem. Maybe this is a... Is my internet down? I think I'm still streaming. This seems like a browser problem. It's interesting. Can I get Apple to stop caching something about my network connection, maybe? Network troubleshooting. We've got everything on this stream. Yeah, I think there was something cached that, because like I'm not running a DNS server on my router now, I'm just having its DHCP hand out like 8.8.8.8, which seems like a better option anyway, so I guess some stuff was still caching the old server. Oh, maybe I just have this in... Maybe I just have the Git repo, actually. Maybe I didn't even need Google. Oh yeah, it is an Eagle. I thought this was an Altium for some reason. But, that's great. That is the glitching section. I want the acquisition section. Well, I think that was the right section, but I would like some assurance that this is actually going directly to the SMA, because I don't see the SMA connector itself on here. Hi, train. Okay, so that's connected directly to L11, C68. Huh. I mean, I'm no analog guru, but that does not look 50 ohm terminated to me. I mean, that resistance seems to be closer to what's going on, but I mean, it's also AC coupled. Excuse me. Well, I might just try measuring it with a voltmeter when it's off and see what that looks like. Yeah, I'm not super happy about the Eagle subscription licensing. I mean, you know, I get the thing where software developers gotta eat. You know, that's been me on the other side of that too, but the way subscription software involves kind of exerting force over your users, I don't think that's going to end well. So you know, it's like one of those rooms that I'll duck into, but I keep my eye on the exits. So it's kind of how I feel about subscription software. Like, I'll use it, but I'm really nervous about relying on it. All right. Maybe I'll actually close this slightly cleanly instead of just yanking the cable. Okay. Okay, let's just do a really quick resistance measurement. I'm sure this is not the most accurate way to do this, but it'll give me an idea of what I'm dealing with. Yeah, it's not stable. I mean, that's not giving me a stable reading, but it's fluctuating around in the mega ohms. So that would be about right for a DC reading, I guess. So that's interesting. I feel like I might get a better signal if I put a 50 ohm resistor across there, and then put another like pair of series termination resistors on the other end. Because right now, I mean, I've got a pretty low impedance path between power and these SMA connectors. And I just feel like that's probably just gonna, I don't know, just give me a really dirty signal full of reflections. And then on this side, ideally, I think I would have, so I've got these two SMAs, which in this case, I'd like to use one of them for the chip whisper and one of them for the Oscilloscope. And this capacitor's a little bit in the way, but I can get that out of the way and then add resistors in the right spots. Oh yeah, these are these probes are new, courtesy of one of my viewers, Focus. Big improvement. I'm quite grateful. Okay, might not be able to focus quite that distance, but yeah. Yeah, that's much better than the other probes. Nice and sharp. Okay. I'm going to grab some surface mount resistors if I can find the right size. Ah. Oh, okay. There's our 47 ohm resistors, 1/8 watt, 0805. So I think I want to make a little removable shunt I can put on the chip whisperer side first. Yeah, I'll just put a little jumper thing right there. It's tempting to modify one of these little shorting jumpers to have a resistor in it. Oh, I mean, maybe I'll just solder one on. It might be just easy enough to desolder it later that I shouldn't even worry. Ah, the cat's in position. Yeah, I'm still thinking about how good the peripheral was, the William Gibson novel. I just finished it recently. And it's, I mean, it's kind of bleak, but in this way that, I don't know, it makes a lot of sense. It'd be interesting if we, I don't know, I feel like we don't have a lot of visions for the future that are like optimistic and realistic at the same time. But maybe that's just the way things are right now in time. I guess I could be using the microscope camera for this. Oh, where did I put the microscope? That's not helping. All right, ground plane. I guess this might be a reason to use a connector instead of soldering the resistor directly, but it's too late now. I mean, it would be fine. I mean, I don't like modifying my chip whisperer, but it is easy to modify, and this is like not the first thing I've changed on it. I also, for this experiment, ended up removing the built-in glitching MOSFET so that I could have a glitch output with, you know, without the capacitance of the MOSFET gate hanging on there. Soldering iron is having trouble with this. Turn it up slightly. That might do. Ugh. Let's add some flux. Okay, that's not going to be amazing, but I think I'm going to stop fussing with it right now. Okay, 46.9 ohms, which is close enough to 50 for my feelings right now. It's definitely going to be better than the way this was before. So let's try making a similar modification to the other side, where we series terminate instead of parallel this time. Ah, this desk is so clean. Okay. Do need to bring the microscope a little closer. Isn't it weird how President Obama just left the White House with nobody in charge? I thought it was pretty weird. Like, usually they're so careful about that. Like, the Secret Service is all like, we gotta have an adult here. And now they're just like, well, actually, there was no rule about having an adult here. That was just tradition. Cat keeps moving. All right. I guess he's moving back anyway. All right. The way I wired this is a little bit inconvenient. I might just take off this capacitor temporarily because this thing is in the way. I don't even know if it's that helpful. Okay, so I want these two no longer to be kind of connected in series like that, since I want them each to have their own termination resistor. But they're still both going to go to the same place after the termination resistor happens. Maybe let's just take that wiring off. Okay, maybe there's enough epoxy right on that joint that it would be easier to do this slightly differently. So let's maybe keep that as a place to sit the resistor. Okay. So these flat cable connections are really doing the same thing, but I was I was doing everything I could to reduce the inductance and resistance of those, since that's what's actually carrying the glitch signal. I mean, not the trigger, but the actual current that flows during the glitch. So that's going right from this MOSFET, which is actually responsible, through this little flat cable to pretty much the closest convenient spot I had to the relevant pins on the board. So I think right now I just want to stick resistors on there, and then stick some relatively thin wire from those resistors to that test point, just so that, you know, I don't need it to be thick, and thinner wire will be less damaging on the resistors. little bit of epoxy on this wire, making it not so solderable. So I just need to clean this off so I can attach the resistor. Like, once I can actually heat up the wire, then the solder should start attaching. Pressure. A little bit of pressure. Cool. Okay, yeah, and now that's like the connection I wanted in the first place. So, I guess it was under less epoxy than I thought. Enough to make it hard to solder to, and not enough to stay in one piece once the soldering begins. But that's fine now. Let's see if I can do a similar cleanup on the other side. Yeah. Okay. More resistors. So I think after getting these resistors on, I just want to do a side-by-side comparison of what the signal looks like through that same scope probe and through the cable with something like a proper 50 ohm termination. I sort of saw where that went. It seemed to fly horizontally somehow. Such a thin line between a useful component and a piece of conductive debris. I mean, I don't see it. I could just blow the whole thing out with compressed air again. The compressor is not on, and I don't think there's much in the tank right now, but let's see if this helps. Ah! I saw the resistor escape. 470. Those are both bad solder joints, but I'm gonna keep going and touch them up if I need to later, because they're hard to stabilize at the moment. Cutting two little pieces of 30 gauge wire wrapping wire that are about the same length. It's not that important that these channels are matched, but it would be nice. So. I mean, if I really cared about that, I would be using higher precision resistors. I mean, at this point, I'm not totally sure how much of the experiment I'm going to end up wanting to run from the Oscilloscope versus from the chip whisperer. And it might just be that I end up mostly using the Oscilloscope, but you know, it's pretty easy to get the signal to both places if I need to, so. I mean, I already had both of these SMA connectors glued to the board. Okay. It's not amazing, but it should be fine. And those both want to go in the same via, well, test point, really. All right. Cool, about 50 ohms from each. So, I think I already have a cable with the right adapter bits for this. Got a few different BNC cables to choose from, but I think let's try this one first. That's a little too much sunlight. That wire is too short. Got some longer coax that I got for video, but it might be close enough for this. I think it's 50 ohms. Alright, Oscilloscope on the left and Chip Whisperer on the right. This. Alright, clock should be running. Now we need to restart the FPGA thing. Okay. And power on. And network. Cool, and there's our test running again. So the signal looks pretty similar. A little more confident that this isn't just full of reflections and junk. This part of the signal looks much cleaner. Interesting. Alright, let's see how it looks on the Oscilloscope, especially in comparison with the regular scope probe. All the buttons are in completely different spots than I'm used to. It's gonna take some learning. Okay. I'm just going to hold the yellow, ooh, ouch. I'm gonna hold the yellow probe up where I was before, and the green is going to be the coax that we're comparing it against. Whoa, that's weird. Let's go back to the computer. I don't think I changed anything, but now I'm seeing this pulsed pattern. So that signal that I've been assuming was related to the CPU activity, now it's looking completely different. And I'm seeing not a lot going on here, and then that 7 megahertz or whatever signal is showing up very occasionally. So now I'm wondering if maybe that's oscillation in the linear regulator, which was a problem I was having before. I thought I took care of it, but maybe that is actually what's going on here. Because if that's just oscillation in the power supply, then maybe this much lower level stuff is actually the CPU activity that I'm looking for. And it's been difficult to tell the difference between noise generated by the power supply and by the CPU because they're both correlated with the CPU activity. But yeah, maybe that is power supply related. Anyway, let's continue with getting this on the screen via both probes to compare them. Okay, DC coupled and 1 meg right there. Looks like I'm getting, oh, sorry. Looks like I'm getting lower noise on the one with coax, which is not a huge surprise. Well, I'm also getting, yeah, there's also a 50% or a 2x change in amplitude because of the, there's effectively a divider with 250 ohm resistors. So that's actually comparing apples to apples, and the amount of noise we're getting seems pretty similar. But let's look at something more interesting. That's nice. Let's keep that ground. And well, that's great. I think, man. I bet that's the power supply oscillating, and it's pretty cool that I can see it so clearly. It also looks like we're getting pretty much exactly the same results from both probes, so I'm pretty happy with using the coax for the rest of this. Cool. All right. So, so for stabilizing the power supply, I've got this bank of capacitors that my glitch board should have connected anytime I'm not glitching. Let's see what they look like right now. So this is that same like 1.2 volt rail, but I'm probing it right on the capacitor bank. So the capacitor bank is doing its job. This could be an issue with the wiring or with the MOSFET. I'm guessing the MOSFET has a lot more resistance than the wiring at this point. Looking for a ground that I can use to probe on that side of the MOSFET. Okay, yeah, and that's on the side of the MOSFET closest to the processor. Huh. Let's probe just on this side of the cable. All right, that's like the exact same signal, but like 5 millimeters left. Yeah, that and that are just different sides of the MOSFET. Oh. Okay, and that's the bottom of the flat cable. Man, so what's it like just at the bottom of the flat cable versus the top? Yeah. That's just between... Let me just see if I can move the camera, because you're really not seeing my probe positions as well as you could. Excuse me, Tuco. Well, noise from a wildly oscillating power supply would certainly contribute to the glitches not being as reliable as they could be. All right, a little more like stuff in the way here. All right. So you zoom out a bit. So this red cable is headed to, maybe I should use the red channel on the scope for that. I don't think I have a green cable handy, or I would just do that. I guess there probably isn't an easy way to just copy this setup. That's prettier. Yeah. Those look like little chirps of oscillation building up, kind of shifting frequency and dying down. Okay. Now the cable matches the channel on the scope. Clearly that's important. All right, so that's back to both channels, probing. Oh, just trying to illustrate where that was actually pointing. There we go. With a good ground, please. Yeah. Okay, so you can kind of see where I'm probing now. It's right at that solder joint where the two B and C connectors join the test point on the circuit board. So we we're seeing pretty much the same oscillation waveform. But now if I probe up here, which is the same net, like that should be the same signal, I'm just grabbing it up here instead. Now the oscillation is much lower amplitude. It's like about half. And then if I look over here, this should basically be the same signal also. It's also pretty much lower. More noise overall, but less of this particular oscillation. And then this is a little bit cheating because it's on the other side of a MOSFET, but this is the capacitor bank that's trying to smooth out that particular noise, and it's just not even seeing the noise that's left. So I think the way to solve this easily is to add a little bit of capacitance right at the base here, like on the circuit board where there used to be a capacitor. So like right where that flat cable is connected, there used to be a capacitor that I removed so that I could, insert glitches instead. And I tried to replace most of that with this capacitor bank up here that I can selectively disconnect during the glitch, but it looks like that just is too far away for some of the oscillation that's happening. So, like, this was already my best attempt at making the cabling as low inductance and resistance as I could, but I think if even just like an inch of cable is giving me problems, adding some local capacitance might be my best bet. So let's see what I've got that might help. I guess I'll just start with a 0.1 microfarad cap. This regulator is designed to have like a couple of microfarads of capacitance right next to it. And so I've got a couple of microfarads up there, but more than it needs probably. But it seems like having at least a little bit of capacitance right next to it is necessary. Alright, I think I'm just going to stick it on what remains of those pads on the circuit board. Okay. Always gotta remember that gotta make sure the right parts of the circuit are turned off. Because it's tedious to turn off and turn on the entire thing, but I want to at least turn off the parts I'm working on. That's my best bet. More illumination. Yeah. Illumination is great. The first signal I had to take a look at on the new scope, because it was already, you know, on a 50 ohm BNC or a 75 ohm at least BNC, was an SDI video signal. So it's all binary and you can't really see much because it's all scrambled anyway, but I mean scrambled for like DC biasing, not for like encryption. But just saw this beautiful eye diagram. It's really nice actually being able to see these signals. It's also tempting to look at the wrong monitor, and then I would have lag, which would not help my soldering. And then there's that feeling where you put down, here's the capacitor. I put it down in the microscope so I wouldn't lose it. I'm gonna switch hands. I haven't been super diligent about checking this stream for technical problems, but I hope it's been working out fine. I'm feeling the need for a sandwich coming on at some point, so I might have to wrap this up and get some food soon, but one of my first orders of business is going to be to check out how well this one worked out and make any adjustments I need, and then do some more of these. Because, you know, seems to be what I do. It's actually, I don't know, it's this weird mixture of being really easy and really hard. Because I find interacting with people in general to be super challenging. So there's this amount of kind of storing up social, you know, abilities and then kind of releasing it all at once. But it's also, I don't know, a much more controlled environment than the real world, whatever that even means. All right, let's see if that helps. So, power. As soon as I plug it into the scope, I get something. It is now oscillating continuously instead of discontiguously and at a lower frequency, which I think means that I still need more capacitance. 4 megahertz. But I think that makes it pretty clear that this is an oscillating regulator. About the same frequency, regardless of whether the processor is in reset or not. Maybe that kind of 10 hertz or so signal that I was tracking down earlier on the stream was related to the regulator also. Well, because there we're seeing something similar. It's not as pronounced. And if I hold the reset button, you know, the overall levels change, but that signal is still there. So it's not coming from anything that's in the processor's reset domain. All right, I think I'm just going to add 0.1 microfarad capacitors until this goes away. And I mean, I don't want to add too much capacitance because the more I add here, the harder it's going to be to get really fast glitch edges. But this is not helping with my glitches. This is just making things unreliable. Microscope. Luckily, those pads are gone, so there's nothing to short with. I mean, that would be a great place to put a capacitor if those pads still existed. All right, so we were at what, like a 3 megahertz noise thing? Let's see what we get now. Ooh, that's nicer. Much lower amplitude. Let's see if we can zoom in on that. Wow. That's like 20 millivolts. I mean, 40 before the drop from the 2 termination resistors, but oh, that's interesting. But I mean, any waveform that is stable with respect to that is not from my processor, it's from something related to the regulator. So I think I need to keep going. Do I dare going to a full microfarad? Or do I just add another 0.1? There is not enough solder in there. Hmm, 0.3 microfarads. a short somewhere. Oops. Power supply was drawing more current than it usually does. I think my V-core is shorted. Where did that happen? That's better. I think there was some solder like right under there, and reflowing it fixed it. Okay, less exciting this time. Oh, sorry. What is it? That's promising. Ooh. And it definitely changes when I reset. I mean, there's still something happening here during reset. So a lot of this seems to be present with or without the chip running, which is interesting. Well, I guess one of the obvious things to do is to keep an eye on the input power too, just to see like what components of this might be coming from the rest of the system. I mean, prior to this regulator. So that is the same net that we just took that big capacitor off of. So if this is messy, I should clean it up, because that could be a big problem in making accurate measurements of just what the CPU is doing if I'm injecting noise from the rest of the system. Yeah, getting a good connection to both the signal and its ground at the same time is always tricky. So the bouncing, that's probably coming from something else on the 3.3 volt side of the circuit board. I mean, I am giving it 5 volts through this linear regulator over here. Let's see what that looks like. That's my 5 volts. That precariously probed thing should be the input to the linear regulator. Hand cam. Huh. Wow. That doesn't really answer my question of where the that low frequency bouncing is coming from, but it is interesting. It looks like the 5 volt and 3.3 volt rails are both bouncing with the signal. The yellow trace right now is my 12.5 volt input supply, which isn't bouncing around, but the noise pattern certainly changes depending on the voltage level output. You know, I wonder if this noise is my 5 volt regulator oscillating. I mean, that doesn't explain the low frequency stuff, but some of the high frequency stuff might be that. Let's try. Actually, let's keep that probing the 12 volt rail. And I'm just going to unplug the 5 volt output from the device under test. That was also my trigger signal. Huh. So that is with the output of the regulator disconnected. Let me find a way to probe this such that I can easily pull out the whole regulator. Alright, maybe I'll just use a little extension wire or something. Oh, I guess I can probe it on this little meter over here. Okay, so that's my 12 volt power rail. I have my device under test completely disconnected, but the only things still on there are this little voltmeter that I have on here just to show the voltage and the regulator itself. So if I just yank off the regulator, ooh. Here I am just touching the regulator, and that changes the harmonics quite a bit. I'm guessing this thing is oscillating. Well, it seems to change if I touch these wires. probe it over here again and then try removing the voltmeter thing. Oh, and I guess I still have the MOSFET driver board connected too. Shouldn't have anything active on it, but, you know, I mean, it has amplifiers, which I guess could oscillate. Okay. That's probing the location where the regulator would usually sit, getting its 12-volt supply. Unplugging the voltmeter didn't change that significantly. In fact, it just increased the noise a little bit. I lost track of that low frequency signal though. The one that was like 10 hertz or so. That one, did we lose that one when I unplugged the regulator? Or is that something else? Okay, that's the voltmeter thing. I'm gonna lose this voltmeter if this thing is getting in the way. It's not helping. Simplify. Okay, it's just the 12 volts. Now let's put the regulator back in. Less overall noise, but that frequency is still there. Let's make sure that isn't coming from the MOSFET driver board. Like, I really need to just like track down where this noise is coming from. So I do not want this in my measurements. I think this is what was, like, it's significantly higher amplitude than the actual CPU, the kind of CPU correlated stuff I'm looking for. Okay, this should be just my linear power supply. Nothing else except for some wiring. Yeah. So, okay, that seems fine. Like, it could be cleaner, but none of that is the particular noise that was getting in my way earlier. Alright, now that should be pretty much the same thing, but with the MOSFET driver board attached. And I think that's just picking up EMI from the cabling. Try disconnecting it further over here. Huh. All of that garbage seems to be actually... Huh. I mean, I don't know if I'm actually generating that noise on the board or if that's just kind of a transmission line effect of connecting this board to the noise that already exists on the power rails. But that's still not showing me my low frequency noise that I was looking for. I was specifically concerned about that because it's going to be difficult to filter out, whereas the higher frequency stuff, I can probably just use an RC filter. So... And then that's also the 12 volts, but now with the regulator attached. That is interesting. Is that my low frequency noise? That's the waveform I'm looking for underneath. I mean, if you look at that steppy pattern underneath all the noise, that's the one I was looking for. And if I pull out the regulator, does that go away? Hard to tell definitively, but seems like yes. Let's try putting the regulator back in. I mean, this regulator has every right to oscillate because I'm not operating it with enough input capacitance, I think. It's just super weird to see this, like I wouldn't have expected such a low frequency waveform unless it's, you know, something other than the oscillator, or the oscillator, something other than the regulator's main feedback loop happening. All right, so I think I have a couple of things to do. I think I need to pay much more attention to power supply filtering on this and put some decent filtering both on this 5-volt regulator, just a little bit off frame. So filter up that thing quite a lot more, and then also filter that 3.3 volt rail. Because a lot of the stuff I'm looking at, I was kind of expecting it to be some weird kind of clock related issue, because there's some other clocking issues that I'd like to talk about, because that's kind of weird in the setup too. But yeah, I think this actually might be much simpler. I think we might just be having some power supply oscillation, which could be relatively easy to get rid of. I just have to kind of keep finding the noise and then adding capacitors nearby it, and then maybe additionally adding, you know, capacitors are going to be my main thing. I think I might have to add some resistance or inductance here and there, but I think the first thing to do, though, is add a sandwich to the situation. So I think I need to give myself a short break from the streaming and get a bite to eat, but I will try to resume this as soon as I can. I already learned some interesting things, though, like that. Let me go back to the computer, because I'm still looking at that. Like, man, these little bursts of noise that, as far as I can tell, these are actually just coming from the V-core regulator on the system on a chip. So if I can get rid of those, that would be quite nice, because then I can turn up the gain and be listening much more closely for actual CPU output. And then there's the experiment that I wanted to get to, which I still is kind of still on the plate, which involves modifying the glitch experiment to also be spitting out continuous counts, so that when the glitch occurs, I can look at the timing of those counts and because I still want to know, is this, I guess the top level question I'm trying to answer is, when the glitch works out successfully, is that because of the transient that I'm introducing with the MOSFET driver here, or is it like a secondary clock glitching effect that happens after I destabilize the PLL? And I'm hoping it's the former. I have a suspicion that it's the latter, but if I get to the bottom of that, that'll help me figure out how to more effectively produce reliable glitches, since that's what I'm after. I guess we never successfully loaded those traces, but and I'd still like to plot that data properly. It just involves shaving some more technical yaks, writing a tool to do that, but yeah, I'd like to plot out that data and get like a scatter plot of where the glitches were successful and where they weren't. But from just looking over that data a little bit while it was gathering, I don't think there's as much of a pattern to it as I'd like. So that's why I think the hardware needs a little bit more shoring up to get it to be more reliable before I can get really nice looking plots. So I think that wraps it up for this particular stream. Let me do a quick check on the chat to see if there's anything I missed or any last minute questions I can answer. I let this laptop run out of power. Oh yeah, it is out of battery. I had this plugged in, and then I think Tuco was running past and knocked the cable out, and then I forgot to put it back in. So yeah, I guess my computer that usually has the chat is not booted. If it went to sleep, or if it actually just lost memory. Yay! I was trying to catch up with the stream enough to answer questions, but oh, maybe it's getting there. All right, I think I'm gonna try debugging the rest of this offline. I will get a bite to eat and take a look at the stream archives and see how things went. But thanks for joining, everyone. If you want to be sure to catch the next one, I stream kind of my personal lab stuff on YouTube. You can find me as Micah Elizabeth Scott or Scanlime, and I'm also simulcasting the Senrio related stuff to Senrio Labs on Twitch, so you can join me either of those places. Thanks for tuning in. I'll see you next time.